Uh, Good morning, everyone. Firstly, Tony, great update on Viper and some introduction to Trident drill. This particular presentation is gonna be focused solely on Trident, which is part of a Viper and also Prime 1 mission. Firstly, I wanna acknowledge all these folks that you see at the bottom. This is just a Trident team, which spans not just Honeybee Robotics, but also NASA, Ames, Johnson, and Kennedy. In fact, project manager Jackie Quinn is at NASA Kennedy. The drill is gonna first fly on a Prime 1 mission also to the South Pole on a IM-1 Intuitive Machines a lander. It's mounted on a side with the M Solo at the bottom of a drill for looking for volatiles. So this is going to be our first step in drilling in a icy soil, and a very good step towards learning how to drill for Viper rover, which requires us to drill not just one hole but several holes during the 100-day mission. Prime 1 is going to have just M Solo, no nervous or neutron spectrometer. On the other hand, Viper mission, as Tony mentioned, will have 3 other instruments that are sort of a part of the exploration that includes Trident, and those pictured on top. These are the locations. So Prime 1 is going to be at 11 o'clock, if you look down by Shackleton Crater, right in the South Pole. Again, not inside, but more on the rim. And Viper is going to be also around 11 o'clock from a Nobile crater. There are a few requirements that you obviously have to meet in order to find perfect landing site. It's not just about volatiles, but it's also about access to Earth for communication. It's solar energy both on Viper and also Prime 1. And obviously it has to be a safe landing site. So pretty much everything, all the steps that we take in terms of landing on Mars, we also have to take in terms of landing on the moon. Concerning a history, we've done some drilling on the moon previously. We've done it with the Apollo astronauts, Apollo 15, 16, and 17, drilled down to 3-meter depth and captured core samples. But also Soviet Luna 16, 20, and finally 24 drilled down to 2 meters. So in fact, the deepest robotic mission was Luna 20. It was sample return mission from Crisium back in 72. They really drilled down to 2 meters and captured sample. Since then, nothing really happened. The next one was Changi 5 in December of 2020. It used pretty much exactly the same approach that Luna 20 used in 72. So this shows that if you've done something right, other folks will follow will use this technology, and that's what happened with Changi 5. The purpose was to drill down to 2 meters. However, the drill stopped at 1 meter depth. It hit a rock. It didn't have enough power to percuss, and the samples were returned from 1 meter depth. Next up, obviously, is Prime 1 and Viper. The dates have changed a little bit. And then Changi 6 also is gonna go to the South Pole. The Prospect, it's a European drill with a mass spectrometer, is gonna also fly on CLIPS mission in 2025 or 2026. And just down below, we are flying 2 other drills which do not penetrate icy soil, but they still go below the ground using pneumatic approach. These are heat flow probes. They're going to 3-meter depth. The drill is called Lister. It's a heat flow probe with Seiichi Nagihara as PI from Texas Tech. And then Artemis will have drills too. And Lupex, which is a Japanese/Indian mission, will also attempt to drill a few meters below the surface. The drill itself weighs just over 20 kilograms. And it always surprises me that avionics required to run a drill is at 25% of the mass of the drilling system. So I'm a mechanical engineer, and I usually look at the metal as being heavy. I could never think of electronics weighing so much, but that's something that we always forget, mechanical folks. And when you develop hardware, do not forget about electronics, okay, that runs your hardware. This stuff is obviously required. Do not forget about harnessing. Do not forget about cables. All of this stuff adds up. And our avionics box is around 7 kilograms to 25%. The drill can penetrate just more than a meter depth. It's approximately 1.3, 1.4 meter long. So he obviously sticks out about the rover itself. The bit diameter is 1 inch or 25 millimeters. We have implemented so-called a byte sampling approach, and there is a science and engineering requirement why we did that. From a science requirement, we want to preserve stratigraphy. So we drill 10 centimeters down and we pull up material, we dump it on the surface where MSOL or nervous, they can view it and analyze the 10 centimeters as it's being dumped on the surface. And then we go back down for another 10 centimeters. In these bytes, we also stop, we preload the bit against the bottom of the hole, and we take temperature measurement. So we take temperature measurement with no cuttings when the drill is somewhat ice soaked. From an engineering perspective, it also makes sense. This is the graph that shows values on the y-axis and depth on the x-axis. And I would like to focus on the blue curve, which is power. This is pretty much the same icy soil from around 10 centimeters down all the way down to 1 meter depth. What you see is the power initially stays constant and then starts increasing. It doesn't increase because you start drilling into harder stuff. It's increasing because the power required to move cuttings to the surface is higher and higher and higher. So at the 1 meter depth, you need twice or 3 times as much power to move the chips to the surface as the power required to drill. And for that purpose, we do byte sampling approach. In this particular curve, the power is on the left-hand side on the y-axis, and you can see that it stays under 150 watts as you go deeper down. So thanks to this sort of approach, the power is pretty much stable. And as you know, in a Changi 5, the reason why they couldn't drill down to 2 meters was because power. All right, they had to go in a one go all the way down to 2 meter depth. So that's how we're saving power and energy. Finally, the drill is not just this thing that brings stuff to the surface. It's also a scientific instrument. It measures temperature. It measures bearing capacity. It can also do thermal conductivity with an embedded heater. We have a heater in a drill. And finally, it can tell you how ice is distributed in a subsurface. It will tell you whether ice is mixed with regolith, so it's really easy to excavate, or whether ice is ice cemented, like in Alaska in winter, as hard as concrete. No other instrument will tell you. And this information by itself has fundamental effect on how we're going to do ISRU in the future. If it's icy soil with ice mixed with regolith, you can just scoop it up. You don't need big explosives and huge excavation systems. But if it's ice cemented, you have to look at a different way of doing it. Finally, this is something that I would have never expected when I started my space career back in early 2000s. It took several generations of developing of this drill. So when we touched down on the surface of the moon, it would take 20 years to develop this drill. Initially, we started with a Crooks lunar drill. Funding got cut, so we switched gears and we started developing drills for Mars. So it was Icebreaker, Lita, then back to the moon with the Resource Prospector. And some of you may not remember, but RP was canceled for a year and then became Viper. So it took 20 years. We are fortunate that these days things are moving way faster than in the past. So folks of you who are starting your space career, Don't be alarmed. Okay, you won't have to wait 2 decades to see your hardware on a moon or on the other planetary body. Things take much faster these days. All right. So I know I think out of time, so I'm gonna end here and happy to answer some questions. By the way, Jack Schmidt on the left-hand side, he came to visit us. He is a frequent reviewer of our hardware. On the left-hand side in a clean room, you can see the Prime 1 drill. On the right-hand side, between Jack and myself, you see a Viper drill. So the stuff exists, okay? And in the next, I think 2 months, we're gonna be wrapping things up. Thank you.